Shall we get started? Buck, am I good? Okay. The class is thinning out in lecture, but nobody's dropped. It's good to know. Good to know. Okay, so we are in between spring break and carnival. And so what we've been doing is we've been going on this series of lectures that sort of had this theme. We talked about how communication was implemented in hardware. Then we went back into software and said, well, if you want to synchronize or communicate with locks or barriers, here's how you might implement them. And here's how your various implementations will impact all the messages that get sent over those interconnects. Today, we're going to talk a little bit more about writing data structures or thinking about algorithms where we're trying to alleviate contention amongst all these threads as much as possible. And tomorrow, or not tomorrow, but Wednesday, we're going to talk about new abstractions or new mechanisms, much more modern mechanisms that are appearing in hardware just now, just today, or in the last couple of years, to potentially make it easier to synchronize a bunch of threads. And then we're going to pivot. Starting next week, we're going to really pivot away from kind of the basics of parallel computing into a whole bunch of modern topics for the rest of the course. So we're going to start talking about what's in an iPhone on Monday and stuff like that. And so it's going to be all pretty modern stuff. And so hopefully it'll be enjoyable. Okay, I do want to remind everybody that tomorrow night at 7, Professor Raylene is giving a bonus lecture. It will not be taped because Buck probably wants to be at home because it's at 7. So you've only got one shot at it unless somebody wants to bring a webcam. More than welcome to. And Professor Raylene's going to talk about a number of things, but the key topics are going to be how do I think about debugging the performance of my program? Sort of, we're watching some students in the class be like, well, it doesn't run fast. Not sure what to do next. And there really is like some methodology that you're picking up on as you're doing more and more of these assignments. But there's really some principles that those of us that have done this for a long time know, and he's going to talk about that. And then he's also going to talk about useful tools that are out there in the real world to help you debug the performance of your programs. And so these tools might be very useful to you, probably not actually in assignment 4, but in your projects. And some of those tools are about capturing traces and things like that, which could influence a project that you decide to do. Like, for example, Karima, one of the TAs, used one of the tools that Brian's going to talk about, PIN, to capture a big memory trace, and did a whole project last year on simulating the behavior of cache coherence in a simulated processor that she implemented, using these traces to drive that machine. So if you know about these tools, you might be like, oh, I have an idea for a project now. Any questions about what's going on in the world? How's assignment 4 going? It's going? Okay. It'll go a little slower when there's 100 people in the queue, so let's try and push it a little bit. Hey, I asked you, everybody, about this slide last time, and I said let's discuss it in the beginning of class, but I also said let's discuss it on the web, and nobody posted a darn thing on the web about this slide. So we're going to burn lecture time to think about it a little bit. So does everybody remember how we finished the lecture last time? How we finished the lecture last time is I said, I put this barrier up there. I put a barrier implementation up. And I said, this code is broken. And this code was broken because like any barrier, the point of the barrier is to hold up all the threads until they reach the barrier. And then as soon as all the threads reach the barrier, you can think about it as the threads being released to continue on in their execution past the barrier. That's what a barrier does. And does anybody recall what the problem was with this implementation? What was the problem with this implementation? That's right. So the main idea of this implementation is very straightforward. If we're going to implement a barrier, we need to count all the threads that have arrived at the barrier. And that was every time a thread arrives, we increment the barrier's counter. And then when enough threads had arrived, when the number of arriving threads was equal to, let's say, all the threads, p, we reset the counter to 0, set a flag that all the threads would spin on, and say, OK, when the flag's 1, that means that, that I can go, that I can proceed past the barrier. And the problem here was that a thread could leave the barrier, reach the next barrier in the program, and call this function. And then all of a sudden, before some threads had observed that they had left the barrier in this while loop, some other thread may have already reset the counter to 0. And so we could get ourselves in a deadlock situation. And so we fix this. We fix this at the end of the class by actually making 2 counters. And the gist of the second counter, if you remember, was saying, hey, before any thread enters the barrier, it must check to make sure that all threads had left any previous version of the barrier. So everything's still the same, except as threads are now leaving the barrier, the leave counter is incremented. And any thread arriving at the barrier will check to see if the arrival counter, if the leave counter is full, is p. And that means that there are no threads left in the barrier, and it's safe to reset the flag. So I asked if anybody could think of a more elegant version of this code. And some of you may have been immediately thinking back to a barrier implementation from like lecture 2 or 3 that avoided having to spin in 2 different places and avoided the messiness of these multiple counters. Did anybody think about this problem at all? No? Did you think about it? Yeah.
All the threads have arrived, and then maybe that one could wait for all of the rest to leave, and decrement that and arrived, and once it hits one, until it hits one, the last thread just spins.
I could see how that would be an approach towards a solution. Another way to think about it, I could see how that would work, but you're still going to have kind of 2 counters, because now it's just one thread is sort of counting down. So you're still kind of counting down and up and things like that. So what is the problem here? What's the fundamental essence of the bug? Yeah. That's right. We have a dependency. We have conceptually different barriers. And we have we're kind of like sharing the state across those 2 barriers. So if there was any way to replicate that state, we'd be in better shape. And if you remember way back at the beginning of the course, we kind of did this when I said, hey, can you do this? Can you change this program that had 3 barriers in it? Could you change it to a program with 1 or 2? I can't remember. It was a single one, right? And so that's kind of what should be going off in your head here. I want to detect it when a condition's true. And I don't want that same condition to apply to 2 barriers. Yeah?
You fix this by just having one more flag, which could be swapped on and off, depending on how many. If this is the first barrier, the second barrier, the third barrier.
Yeah, exactly. And I can do it even easier than that by just saying, hey, look, should we wait for the flag to be 0? Or should we wait for the flag to be 1? So the first time through the barrier, you set, when you enter the barrier, you say, hey, I'm going to wait for the barrier to be 1. And then when all the threads get there, the flag gets set to that bit. The flag gets flipped. And then the next time through, you can say, oh, I want the status of the flag to be 0 now. And the last one through flips the flag. So this is very much in the spirit of what everybody was suggesting. I just wanted to point it out there. This is called a sense reversal barrier, because you're sensing, you're waiting for a flag to take on a value. And depending on sort of the parity of the time you hit the barrier, you could actually wait for a different value, which allows you to actually get by with a single flag to have 2 purposes. But you could just as easily have thought about it. So maybe we'll just have 2 flags. and the sense tells me which flag to look at, which would be essentially equivalent.
Maybe this is like a more complicated situation overall.
It may be.
There's a barrier here, all the threads go to it.
Okay.
And then there's branching. Some of the threads hit one barrier and some of the threads hit
Okay, so yeah, that's a more complicated situation. What I've assumed in this particular implementation was that all the threads need to arrive at the barrier. And actually, if you remember, like CUDA sync threads has a parameter number of threads, actually. It's a more complicated barrier than this. So I could design this to say, well, no, actually. So if I design this to just say wait for some number n, that still wouldn't work because the conditional control flow that you added actually sort of has 3 active barriers at the same time. So we would probably have to give the barrier like an ID. Like all 3 of them would have to wait on a different flag value. And you'd probably need to use different flags for that. You wouldn't be able to use this trick of the same flag on and off. I would, giving them the 10 seconds that I've thought about it. Yeah.
Increment the value until the number of threads value?
Well, it's complicated in the situation that's proposed because we kind of have half the threads hitting the one barrier and half the other threads hitting the other barrier. So you really do need to keep 2 different arrival counters because there's 2 barriers that are active at the same time.
And this
This one won't work for that scenario because this is one barrier and you're not going to be able to use it in 2 different contexts at the same time, which is in fact the problem that got us in trouble that we were able to fix if we're assuming that the barriers come after each other. But if you assume that like there's a barrier and then some of the threads can hit this path and this barrier and some of the threads can hit this path and this barrier, you're going to need a little bit more state to track that. Yeah. Well, you do because that's the definition of a barrier.
But if you have branching, you wouldn't.
Well, if you have branching, and if you look at CUDA, like the CUDA sync threads, you still have to specify how many threads hit the barrier. So if you happen to say, what you could say is something like, let's say you had an if statement and you said all the threads that took this if, I want to hit this barrier, and all the threads that took this if hit this barrier. I would immediately implement that by saying, as soon as you branched, go figure out how many threads went that direction, and then that should be the parameter of the barrier. If the system allowed that control flow to be possible. Okay, cool. All right, so let's talk a little bit about today's lecture. And today's lecture, you're going to have to do a lot of thinking. And you may have to help me sometimes because these examples are going to be really easy to mess up. So in terms of this thinking, today's running example is not sin x. Today's running example is going to be a linked list. And so I've decided to stare at this code a little bit. What we're going to not think about today is we're not going to think about all the edge cases and insertion and deletion from a linked list, like insert into the head and things like that. So I've eliminated that, and I just want you to think about insertion into a sorted linked list and deletion from a sorted linked list. So let's just look at what insertion is doing. Insertion is keeping the previous pointer and the next pointer. And as soon as we find an item in the linked list that is greater than, as soon as the item in the linked list is greater than the value that I'm trying to insert, we will insert before that node. So I'm going to take prev's next becomes the new node's next, prev's next becomes the new node, and prev's old next becomes the pointer to the next thing afterwards. So this is just standard sorted linked list insert. And delete, it's just deletion from a linked list. We're going to walk the list until we find the node that we're looking for, the node that has value, and we will delete that node. So the previous node jumps to the next node, and so on. Okay, so there's nothing fancy here at all. I took out the edge cases of handling the insertion from the beginning or deletion from the beginning. So we can just think about kind of the steady state performance of removing or inserting things into the middle of a linked list for today. Everybody good with the code on the screen? Okay, good. All right. So now let's think about what happens if multiple threads are operating on this linked list simultaneously. Okay. So let's start by thinking about what happens if 2 threads are trying to insert into the linked list. Are we safe or are we not safe? We're not safe, okay.
We're keeping track of previous and current, and then as soon as like Rn is in the middle of them, we insert.
Yes?
But we can have two guys that are in between two adjacent elements, but they get inserted in the wrong order.
They get inserted in the wrong, oh, okay, yes, okay. Got it, yeah, that's correct. And so is there a bigger problem? There's actually, I would claim there's even a bigger problem. That's a good problem too. Yeah.
We can just break the linked list so it isn't continuous.
And how could the linked list get broken?
The beginning of the linked list pointing to one of the elements, then that element is not correctly.
I'm not sure if you can break the linked list with two inserts. You might be right, actually. I'd have to think. I don't think you can. Yeah, I think I need to give you a delete for you to break the list. But you might be right. I have to. Yeah.
If you have like a sorted linked list, you have a previous and next node.
Uh-huh.
And what happens is two threads try to insert
Into the same spot.
that has the same like previous and next node.
Yes.
And then what happens is one of them will request and will change the previous.
Mm-hmm.
And then will change the previous and the other one will overwrite it.
Yep.
And so the like for one of the list ahead is gone or something.
So we don't break the list. We're going to lose an element. So what's going to happen here is, let's think about this. Let's say that this is our list. And it's sorted. It's a correct list. And thread 1 is going to attempt to insert 6. And thread 2 is going to attempt to insert 7. So it's exactly the case that everybody's beginning to hint at, that the two nodes go between the same two nodes that are already in the list. Okay, so let's say that thread 1 is at this position, and thread 1 has identified that 6 is less than 10. That's good. And now previous is 5, is the node containing 5, and current is 10. Because remember, in insertion, if we go back to our code, which one insert is here, while we have not found a value that's greater than what we were trying to insert, keep walking forward, keeping track of previous and next, right? So we will break out of that while loop when current's value is greater than 6, which is what we did here. Okay? And if this was just a normal insert, we allocate the new node. We make previous's next pointer go to 6. We make 6's next pointer go to what previous's old next pointer used to be. Standard linked list insert. Okay. Now imagine what happens if thread 2 is doing the same thing at the same time. It would also stop here in the list. It would say, oh, I need to shove 7 in between 5 and 10 as well. And, well, depending on who wrote the next pointer to previous last, previous's next pointer, so both nodes 6 and 7 are going to point to cur. We're good. But both thread 1 and thread 2 are going to say previous.next equals the node that I'm going to insert. And one of them is going to win the race, or one of them will come first, and the thread that goes second is the thread whose change will exist in the data structure, right? So the result is if thread 1 updates previous next before thread 2, then all of a sudden I have this data structure, which is a correct sorted linked list. It just happens to be missing one of the nodes that I thought should have been in there. Yes, Isha? If it was a doubly linked list, let's see if we can do this in real time. So if it was a doubly linked list, oh yeah, it probably could, right? Because I could actually go forward through 7 and backwards through 6, right? I think. Somebody should check that and post the code, but I think that's true. I think that's true. Cool. Okay, so good. What happens on simultaneous deletes? What are some bad things that can happen? Yes, exactly. So if you have any delete going on, you might patch up the list by pointing to a node that's being deleted. And then all of a sudden, you just set the previous as next pointer to a node that's not in the list, and you just lost the whole back half of the list. There's another problem with double deletes. There's another problem with double deletes is there's a free somewhere here, right there. There's a delete right here, and you very well may call delete on the node itself twice. And of course, the losing the list problem can occur if you're inserting and deleting as well. So there's some problems with this. Okay, so good. So we jump through here. So what's our solution to the problem? Imagine that you wrote this code, and probably many of us have written exactly this code at some point, right? Like we've written our basic linked lists in various classes. And imagine you fired up some pthreads and used the data structure. Everything that we just talked about could start happening. And so you've taken this class now, and you're like, okay, I need to make this data structure thread safe. And you know from this class that you do the simplest thing first. What do you do, Dave? So you're going to throw a lock around the whole list. Is that the same solution? Okay, so let's do it. Where do you insert the locks? You can try it if you wish, or you can go to someone else. I'll go here because you got that one. So where do we insert the locks?
Simplest way would just be lock at the beginning and unlock at the end.
Lock at the beginning of insert. Lock at the end of the function. Lock at the beginning of delete. Lock at the end of delete. Right? You sure? Inserting locks is tricky. Very close to correct. What did I miss? I just never unlocked my list. List is dead for the rest of the program because it never got unlocked. Right? So, I just forgot one. I needed an unlock here. And because I missed that, now all of a sudden I have a program which some other thread goes to insert. No other threads are in the data structure, but some thread, because of a bug, is holding the lock. Yes? C++, like you're saying, if it goes out of scope? Yeah, so you could have a lock. You could have a class that always went out, as soon as it went out of scope, would unlock. Like, so a common thing to do, it's almost like the same way that people implement smart pointers all the time, which do their own reference counting, and as soon as they go out of scope, they delete themselves. A common thing to do would be to embed a mutex in a class, and the constructor is a lock, and the destructor is an unlock, which means that whenever it goes out of scope, you don't have to worry about these things. Common software engineering tactic. You also now in your code have no clue where your locks are, which can be also cause its own set of issues. Okay, good. So yeah, so this is exactly what I would do if I wanted to get a correct program as quickly as possible. I would insert locks at the beginning and end of insert. I would insert locks at the beginning and end of delete, and I had to be really careful to release my lock in all paths of executing that function. Good. So what is good about this solution, and what is bad about this solution? What's good about the solution? It took us 30 seconds with one bug, probably about 15 minutes to track down that bug, and then we implemented it, correct? What's not so good about this solution? Only one thread can be manipulating the linked list at a time, which, if your program is not particularly sensitive to the performance of a linked list, might be perfectly reasonable. Or, if your assignment happened to be implement as fast as possible a parallel linked list, it could be disastrous. Depends on your program, but exactly, right? So what's good? Relatively simple. We just did it. Bad? Everything is serialized. It essentially is not a parallel linked list at all. So here's a question. Who can do better? Okay, so we have a lot of people down here. Yeah. How are we going to do better?
Make sure that whenever you're updating two pointers for a particular operation, that those two are.
That's right. So we need to make sure that first of all, well, we need to make sure that if we're updating a data structure in a linked list, and this is a singly linked list, so usually the only thing we're touching is the previous pointer and the current pointer. And maybe we might need to worry about the next as well because we're writing pointers to it. We need to make sure that, like, sort of in the sphere around the operation that we care about, no other thread is accessing those data structures, or that part of the data structure. If we went to the very, very end of the linked list, like a million nodes away, we're perfectly fine with some other thread manipulating the data structure over here if we're trying to do some insertion in the front half, right? OK, so absolutely, perfect intuition. Now, how might you think about that? How can we start turning this into an algorithm? Yeah, take it.
I don't know how to like do it with the global but you can have a per node insert block that says, I'm inserting immediately after this element.
OK, good. So we could say that maybe we should take a lock on a per node basis. So we're going to move the granularity of our protection, of our mutual exclusion, from the data structure all the way to an individual node on the data structure. So let's say a starting point in the conversation is maybe whenever you visit a node, let's say you grab the current pointer, let's say you grab the lock on it, and then you continue on. Is that good enough? It might be kind of hard to think through this in our head. We might need to move to a visual representation shortly, but is there anything you wanted to add? Yeah. That's true, because if I'm going to read it, while I'm reading it, it could be deleted right then and there, right? So I have to be very careful about what I'm doing. Yeah. Well, they certainly could, actually. I mean, so right, because if I'm trying to delete a node, and any other thread comes in there, unless I'm synchronizing the threads at that node, I mean, I have no guarantees what somebody else is doing to that node, whether they're removing it from the linked list, whether they're deleting it, whether or not they're changing the next pointer because of an insertion. Yeah. You can say a read lock or a write lock. So right now in this lecture, let's keep it simpler by just saying all locks are just total reader-writer locks. But there will be some ways to optimize things by saying there can be multiple readers to this thing, but only one writer. That's definitely going to be the case. Yeah. Yeah, I think that's a reasonable thing to do. So let's take all the ideas that you guys have said, and let's try and embody them, at least visually. So let's say that I want to remove, what was the problem? I want to delete 11 from this list. So one answer might be, I'm going to lock the list, take the lock on 11, and then delete it. So what could go wrong if all I do is I walk through the list, I lock 11, and then I start the deletion process.
If some other thread was trying to insert right before 11 or right after 11, it might screw up.
Yeah, so if I was trying to, let's see here, if I was trying to insert before 11, then the next pointer can point to 11. And then boom, I just removed 11 and I just cut the back half of my list just off. Reasonable, good example. Yeah. So I have to do more than just lock 11. What happens if I locked 10 and 11? Maybe. If I lock 10 and 11, think of a thread coming in behind me. It can't get to 18. Well, I'm just like, so imagine like the base case is I have 10 and 11. I'm holding those locks. And now let's say another thread enters the data structure. So if it doesn't need any of the locks, then I've got a problem because it might try and start updating 11 right when I'm deleting it. But maybe I'm going to force the other thread to also take the lock on 11 before it tries to manipulate something between 11 and 18. And so if the other thread needs a lock on 11, and I'm holding the locks on 10 or 11, I'm preventing any thread from getting into there. So this is, we're edging towards a solution that has some nice properties. Yeah. Well, if you're reading a node and you don't have the lock, you now have no guarantee that someone else is not deleting it. So even though you're not modifying it, you may be reading deallocated memory at that time, so you're going to have to be careful. Okay, so one way to think about this is think about this as an invariant. The first thing you all are suggesting makes a lot of sense. If you're going to read a node, you better be holding the lock. Because if you're holding the lock, at least other people cannot be reading the node. And so if you can delete a node, by definition you're reading it, so you need the lock for that as well. So here's what we're going to do, is we're going to grab the lock on every node that we read. And then maybe we release the lock after we've seen the next pointer. And then we take the lock on the node. So think about it this way. I take the lock on 3. I'm happy. I release the lock. And then I take the lock on 5. People are shaking their heads. Why are you shaking your heads? Yeah.
Release the lock for 3.
I released the lock from 3.
Then the other thread which could be wanting to delete 5, then it could acquire the lock for 5 and delete it. And
So maybe I read 3, read the next pointer. I released the lock. And before I jump to the target of the next pointer, another thread could have come in and deleted 5. So what does this suggest, and why do you think I have 2 red circles on the screen right now?
Because you're always going to have at least one lock on the list at a time.
That's right. You're going to always have one lock on the list at a time. And we often call this hand-over-hand locking, because it's like when you're on the monkey bars. You're never going to release a hand off the monkey bars, because if you do, there's going to be a problem, right? Like you're going to start falling. So what we're going to do is we're going to take the lock on 3. While we have the lock on 3, we're going to grab the lock on 5. Because if we have the lock on 3, it's not possible for anybody to manipulate 3. We grab the lock on 5, and then we can release the lock on 3 and move on and so forth and so forth. Yes? Yes?
Someone tries to delete 5.
Correct?
But they can't quite yet because they can't manipulate 3's next.
Correct. So we've been kind of just talking about locking the list, and so now there's going to be a little bit more that we need to think about to do that deletion, right? So, but everybody sees how if we do a hand over hand, if we always have a lock on one node in the list, nobody by definition is going to do anything bad to the node that we're on, and moreover, no other thread is going to jump us in the list. So the pointer that we have going forward, or if we get a lock on something going forward, we're in good shape. So we're going to do this all the way till we get to almost to 11. So this goes to your question, well, wait a minute. If I'm going to delete 11, that means that I have to manipulate 10. So if I'm manipulating 10, I better not release the lock on 10 before I try and delete 11. So we're going to do our hand-over-hand locking, and the invariant is going to be, if I'm going to remove a node, I better have a lock on that node, because that means no one's reading it, and I better have a lock on the previous node, because that means nobody is reading it. So if I have a lock on the current and the previous, I now know that no one is reading either of these values, so I'm safe. I also actually know that nobody is deleting 18. Why? They would need the lock on 11. So someone may be reading 18 to be moving forward, but they certainly are not modifying 18. Because if they were modifying 18, deleting 18, they would have the lock on 11. But they don't, because I have the lock on 11. So once you have those, oh yeah. The list?
Yeah.
It's a list. Yeah. So yes. That could.
I don't think we ever had it do that.
As long as you started in the same spot, I think you're okay. I think. Yeah, given this code. Okay, so imagine now that thread 1 comes in. I haven't finished anything, I'm just holding these locks. And the next thread comes in and wants to delete 10. So this is going to hand over hand lock. And what's going to happen at this point in the computation? Thread 1 has to wait because it cannot get the lock on 10. Correct. So thread 0 has everything it needs to perform the deletion. After it executes the deletion, it will release its lock. And then thread 1 will grab it. And then it can perform its deletion. And it will release the lock as well. So in my simple implementation here, which is not that simple, or it's the simplest thing you could possibly do other than a global lock, it's the invariants are, you better have a lock on a node to access its contents, because you don't want it deleted out from underneath you. And if you want to delete a node, you better have a lock on the node, the node you want to delete, and the previous node that you're going to also modify, because the next one. And those are the only two invariants, and that holds for both insert as well as delete. Because if I'm inserting, it's okay I don't have the lock on the node in front of me, because all I'm doing is changing the pointer to that node. And if somebody else has the lock on that node, that's okay, because they're not deleting it. Yes? No, you cannot read the next guy. Because yeah, technically it is safe to read the next guy, because you know that they're not being deleted. So if you have current next cannot be deleted because of the invariant on you need next and prev. So yes, actually, it's probably fine. Not probably fine, but I believe it is fine. So since you know that it's not being deleted, it is safe to put the next pointer to it. And you know that nobody else is inserting in between you and the next guy because you have the lock on the current guy. Yeah. So that's, in our simple linked list, that's, I think, all the cases. Yeah. Yes.
Insert in between in the two spots there.
3 adjacent current nodes. Okay.
Yeah, like 3 nodes in a list. 2 spots. We
Yeah.
don't allow 2 simultaneous insertions there, though that is safe, correct?
It certainly is safe. Would we really not allow it, though? Let's think through this. So let's say we had A, B, C. I have a lock on A. I have a lock on B. And why can't I insert?
If one is trying to insert it to something further than, let's say, a thread writing, it couldn't pass over that thread.
I agree that no other thread can pass those over, but I believe if thread 0 is holding A, thread 1 is holding B. Let's say thread 1 got in there first, got to B, dropped its previous pointer. Thread 2 can come in, hold A behind B, and I think they can both insert. I think. Is that the case that you, yeah. So let's take a look here. So notice that there's a little special case here for locking. There's still a list lock, and the list lock is sort of protecting the first node. But if you ignore that, you can look at this on your own time and figure out why that's there. But in general, it is if current, if I'm not at the end of the list, lock, and release the old one. So release the old one that I had. So you're always holding 2 locks at the top of the list, at the top of the while, and then you release the old one, you're still holding 1, and then you grab the next one. So that is the hand over hand here. So the challenge to the students, to you, and good common opportunity, is there is a way to improve the implementation of insert, and it might be very similar to what you were hinting at. Right? So someone should try and write the code that gives maximal parallelism in insert, because the locks that I've inserted here for symmetry between delete and insert are a little overly conservative in the insert case. Exercise left to the readers. Yes?
When you have insert, should you just check if you succeeded or not? You're trying.
Yes, and we're going to move in that direction. So hold that thought for a second. Okay, so this fine-grained locking solution has some really nice properties. A list is a data structure that fundamentally different threads should easily be able to be manipulating at the same time. And now we've allowed that to happen. That's cool. But we've done it at some cost, right? First of all, it's significantly trickier now to make sure that you didn't mess up. You know, linked list is probably one of the simplest data structures that we'll implement. And we're kind of having to, I'm having to think really hard when you're asking me questions. It's not easy. There's also some interesting costs. So now I have the compute cost of every step in the linked list is now taking a lock. Further, those used to be reads bouncing through the linked list. Now they're all writes. And you know about the implications of that to coherence traffic. And then there's like a storage cost, because like previously my node was 2 words, a value and a pointer. And now all of a sudden I increased its storage footprint by 50% by adding a lock there. So that's kind of So what might be a middle ground solution? So I gave you the coarsest possible lock. I gave you almost the super ultra fine grained locking version. And you know that there's always a middle ground that might mitigate the benefits and the costs. You could very much do this locking at some other granularity, right? Like where you locked at the granularity of 32 nodes or something like that. Yes?
There are meter writing locks that might allow us to traverse over the list with meter locks and then...
Right. It's very possible that you can move to locks that sort of aren't exclusive, but might let multiple readers through and prevent a writer from coming in if there were any readers, which would be ways to optimize the discipline. Okay, so a practice exercise, which we will not do here in class, but I encourage you to do, is try and extend what we've done here to a binary tree. So think about insert and delete into a binary tree. And this, like if somebody wants to be ambitious, post the code underneath the slide. And by practice exercise, I mean previous exam question. So this was something that the students were asked to do, I think, 2 years ago on an exam. And we were like, maybe this is insane. And a lot of students got it. So we were very pleased. OK, so now I want to talk a little bit about making sure that these data structures are safe for multiple threads to be using them at once without actually using any locks. And that's the concept of lock-free data structures. And lock-free data structures are something that's intellectually really, really cool. And be a little bit careful about, you hear lock-free and you're like, that must be amazing. And like in many things in computer science, that's not always true. So we'll talk a little bit about why lock-free data structures are a good idea, and also why, in the late 90s, everybody loved to work on them. And anyway. OK, so one thing I want to differentiate is between a blocking algorithm or data structure and a non-blocking one. And last time, and so blocking is kind of an overloaded term in computer science. Last time we talked about a busy waiting versus blocking, where busy waiting was kind of asking, are we done yet? Are we done yet? Are we done yet? Blocking is taking the thread off the processor so it doesn't make progress at all. It really shouldn't have been called blocking in the last lecture, because in this lecture, both of those are blocking algorithms. A blocking algorithm allows one thread to prevent other threads from completing operations on a shared data structure, and indefinitely. And what that means, like whenever you take a lock, you basically have a blocking data structure, because only one thread can be in that part of the data structure at once, and all other threads have to wait. And it doesn't sound like that big of a deal. You're like, well, we made this fine-grained locking. We're only locking one node of the linked list. I'm going to be done with that operation really quickly, so people won't have to wait very long. So one of the major motivations for non-blocking designs and lock-free data structures, if done correctly, are usually non-blocking, is that there are some reasons why it can be very bad to have a blocking system. And here are some examples here. So imagine in that linked list, your thread took the lock, And then all of a sudden, it got swapped out by the OS. So even though that thread is not running on the processor, it's not doing anything. It got swapped out. It won't run on the core for a long time. No other thread in the machine can make progress in our linked list because the thread that's not running is holding the lock. And so the motivation for a lot of these lock-free things were in environments like in servers where you have tons of threads and you have an OS scheduler always swapping out these processes. You could have problems where even if you did a good job by writing a fine-grained linked list, your performance might just completely screech to a halt just because of something out of your control like that. Another example is what would happen if a thread crashed while holding that lock. That means your data structure is, your whole system is now dead for eternity because nobody else can get that lock anymore. Another example is an operating system does not know when you're in a critical section. And so it might just, it can swap you out in the middle of that critical section however it wishes. Okay, so in contrast to a blocking algorithm, a non-blocking algorithm, or an algorithm, a non-blocking algorithm is lock-free if there's always some thread in the system that can make progress. So in the case where in a lock, if that thread gets swapped out, no other thread, they might run, and they might spend their entire time to run just busy waiting for the lock to get released, and it will never get released because the thread that holds it is not running. In a lock-free scenario, those threads that are running are going to be able to make progress. And it's going to be okay because other threads that are in the data structure aren't running. Because if the thread's not running on the processor, we shouldn't have to worry about it being erased with some other thread that is running. So let me give you some simple examples. And it's a slight diversion here. So here is something that you might get asked in an interview question. This is your standard ring buffer implementation of a queue. I have an array, data, I have a head and a tail. Push adds, increments the tail. Pop increments the head. If head and tail are not pointed at the same element, the queue is empty. How many people have implemented this before? How many people have had Google ask them to implement this on a whiteboard? This used to be like Microsoft's #1 interview question. So here's an interesting question. Imagine that one thread in the system is pushing, and another thread in the system is popping. Where do I put my locks? So there's only two threads in this scenario. One thread is pushing, the other thread is popping. So you can think about it like a queue between two parties. I'm going to put work on the queue, and you're going to suck work out of the queue. Yeah. I only need to lock whenever I change the head of the tail, and that's excellent intuition. Why do we normally want locks when we're going to change something? If someone else is looking at it, or usually it's actually if someone else, it could be actually. In the linked list example, it was if someone else was looking at it. But what's going to happen here, if I have a pointer to the tail, and I conclude that the list is empty right as you're inserting, it's probably okay, because I'll just come back later and push. What happens if I have a pointer to the head, and I conclude that the list is full? Right as you're moving the head because you're popping. I'm going to conclude the list is full, and this is a queue. I'm going to come back later and push it again. So in this case, actually, the fact that someone else is reading data that I might be writing, actually perfectly okay. So the only situation we might need to worry about is if two parties are writing to the data, because we could have a read, modify, write atomic update scenario. And I'm claiming that that does not exist in this example. And why does this not exist in this example?
Because push only modifies tail and pop only modifies head.
Exactly. So one thread is modifying one variable. It's completely the only person that's modifying that variable. And the other thread is modifying another variable. One thread's modifying head, one thread is modifying tail. So this is actually a thread-safe implementation for two threads, given the constraints that I told you about.
But if two things, there's only a single element and they both try to pop.
There are no two poppers. There's only one thread that pops, and there's one thread that pushes. So this is how one might do it with a fixed size queue. It's an interesting exercise to think about how it might work if we do it on an unbounded size queue. So this is kind of your like bread and butter C++ concurrency programmer example. In fact, I got it out of Dr. Dobbs. So, hey, who reads Dr. Dobbs? A few people read Dr. Dobbs. Okay. So here, instead of a statically allocated array of all the nodes, we're going to allocate a new node on push. And one would think that we would deallocate the node on pop. But I don't. So what this implementation is doing is actually the same thread, the pusher thread, is responsible for allocating the nodes added to the queue, and also responsible for deleting the nodes once they have been removed from the queue. And the way it works is that I add an extra pointer here. So there's head and tail, and there's an additional pointer called reclaim. And reclaim is a pointer to all the elements that are no longer in the queue, but have not been deleted yet. And so what's going to happen now is pop is going to work exactly as you would expect. Just pop the last item off the queue and update the tail. Push is going to operate exactly as you expect. Allocate a new item and update the tail. Pop is going to update it's going to pop off the head. Except now, when we're done adding a new element, that thread is going to check to see, hey, out of all the things that I've allocated, can I go ahead and remove all of them as well? So the way this might work, here's an example of a sequence of operations in this queue, is let's say we push 3 and push 10. Well, we'll add 3 and 10, which increments tail. We might pop, which increments the head, but not moves the reclaim and does not free the memory yet. We might pop again, continuing to move the head towards the tail. And the queue is empty when head equals tail. And then at some subsequent pop, well, the next pop returns false because there's no data in the queue. Head equals tail. And some subsequent push adds 5. So it increments tail and then walks reclaim all the way to head, deleting the items. So now we have the same thread is touching reclaim and tail. And the other thread is touching head. And even cooler is the memory allocator for news and deletes are all running within the same thread. So you actually don't even have to multi-thread the memory allocator now, which is actually pretty cool. So this is a neat little trick of now I have a completely lock-free queue, still single writer, single reader, but now it allows for unbounded storage. Yep.
Why? So if when you pop, you also freeze and like don't the reclaimer, do you need a parallel memory allocator?
Well, yeah, because now we have different threads that are hitting malloc and delete.
Oh,
Yeah. And also, you're going to need synchronization because you're going to get people touching the same data structure in one port. And I'll come back to it. I'll think about it later. I actually think you need synchronization in the queue as well. OK, so let's try a stack. This is like one of your canonical lock-free examples, because it's actually one of the few examples in lock-free data structures that I can fit on a slide. And so what's going on here? So we have a stack. It's your standard stack. I'm going to implement the stack as a linked list under the hood. And it has push and pop. So what is push doing? While not done, try and make my new node point to the old top of the stack, make the old top of the stack point to me, essentially push an item onto the stack. So the newest item is now the top of the stack. And then there's a compare and swap. So what is this compare and swap doing? If the current value of the top of the stack equals old top, replace the top of the stack with the new node n that I just created. What's this code trying to accomplish with that compare and swap? Sort of, yes, but right. And what's the philosophy of using compare and swap here? Like, what am I trying to do? Make it thread safe. Do you want to add? Make it. Exactly. I'm trying to detect whether, while I'm sitting here with pointing my new node at the old top of the stack, I would like to make sure that no other thread has either popped the top of the stack or already inserted a new node that has become the new top. And I'm checking that by saying, hey, is the top of the stack the same as as it was when I started this whole process? Because the assertion is that if it's the same, then nobody else has come in and modified the stack, and my operation is safe. The same thing happens here on pop. I'd like to grab the top of the stack. I'm going to grab the top of the stack and make the new top sort of the next node down the stack. And while I'm doing that, I better make sure that nobody else has come in and popped this value off the stack or added a new value to the stack. OK, so this is my first try here. And yeah, so notice the difference between a lock around the stack and this. If I hold a lock on the stack and the thread gets swapped out, no other thread will make progress in the data structure. Now, if I'm in the middle of changing the data structure and I get swapped out, another thread will come in, update the data structure. Its compare and swap will succeed. At some later time, I get swapped in by the operating system, or I run, and my compare and swap fails. So being in the stack, in the data structure, does not mean exclusive. There is not mutual exclusion going on here. There is an atomicity of a sequence of operations that's ensured by the check of the compare and swap. But like many things in this class, there's a subtle problem on this slide. And who knows what that problem might be? OK, so yeah. So the compare and swap is saying, if the values are the same, and in this case, it's not the values are the same, it's the pointer to the node is the same. So it's not values are the same. It's if that, and so that's, at first you'd be like, well, that seems safe, because I can't have two pointers. The fact that the same node with the same memory address is on the top of the stack, that's what I'm using to say nothing's happened. And as you're suggesting, that's not actually true in all scenarios. So let's think through a case. And this is called the ABA problem for a reason that will be very clear in the end. So imagine you had this stack with A, B, and C in it. And we started with thread 0, popped the stack, or began the process of popping the stack. I shouldn't say popped, but began the process. So its local variable, old top, is A, and the new top should be B. So let's go back to the code and look at what's going on here. So we're popping the stack. Old top is the top of the stack when we got started. The new top is obviously the next item in the stack. Those are the two local variables in that thread. And then we're golden if when we update the actual stack's top, the stack hasn't changed. That's what we want to have happen. So if we go to the diagram, let's go look here. So now, old top points to the node A. Think about A and B as addresses of nodes here, not the values in the nodes. Old top points to address A. New top points to address B. And then let's say thread 1 comes in And yes, local variable, same thing. Old top is still address A. New top is address B. And let's say for some reason, thread 1 gets to complete its function call before the compare and swap on thread 0. So that's fine. And after that operation is complete, the new top of the stack points to address B. We're good. And we can push D onto the stack. We can even maybe, OK, right. So we'll push D onto the stack. All this can happen while thread 0 is still kind of dogging it. Maybe it did get swapped out or something like that. And then imagine that thread 1, so remember it popped A off the stack, and now it has this node A. It might push node A back onto the stack. It might reuse that node or something like that. Or it could call free on that node, and then it could call malloc and get the same pointer back, right? And then, so that's the new node that's inserted onto the stack. So conceptually, it's a new node. It might have a completely different value. It's on the stack. And now imagine thread 0 starts running again. It runs its compare and swap. It says, oh, the top of the stack is still A. Nobody must have come in between. So let me set the top of the stack to B, which is what I'm supposed to do if nobody has. And then, boom, we just lost. We just corrupted our stack, right? Because the compare and swap will succeed. So this is often called the ABA problem, because it's a situation where like you'll pop A off the stack, you'll put B back on, and then you'll put A back on. And so there's no way, given how we've implemented the code, to identify the difference between no operations happening and a bunch of operations happening that are very meaningful, but for some reason the top of the stack, the variable that we're checking, has the same bits in it than before. So does anybody have any idea on how they might begin to combat this problem? Yes?
Can we use load length store conditional compare and swap?
Yeah, and that's actually a valid, so you could, but that doesn't guarantee that I've written to that address. So, I mean, I don't believe that that solves the problem, because load link store conditional tells me, are there any intervening writes to address A? And that hasn't happened in this scenario. So I don't believe that just moving to LLC solves your problem. Brian, am I? What?
You're looking at the top.
Oh, right, because your load link store conditional is on top, not on A. You're right. So you would know you failed. It's a great question. Let me think about this. I mean, I don't believe, I'm missing something. I don't believe this will solve your problem. Because ABA exists all over the place, and a lot of systems implement load link store. I'm going to have to take that one offline. I don't know the answer to that question. Good observation. Good question. Good question. Don't know the answer to that question. Yes?
Counter on the stack, and then like whenever you do an operation, you'll increase that counter. So when you do the compare and swap to like move the top to B, you want to make sure that that counter has not changed, and because thread 1 has done things, that counter will have changed already.
So what you're saying is that you would like every operation on the data structure to mutate it so that it becomes identifiable that it has mutated.
Yeah.
That's a reasonable strategy. Now, there's one complex thing that you have proposed that's actually kind of hard to do. You've now proposed that I need to update that counter.
Yeah.
Or I need to check that counter atomically with updating the top. So you just basically what you've proposed is you've proposed a need to do a double compare and swap. In that you have to both atomically compare and update the counter and compare and update the top at the same time. And you can imagine that, well, maybe this magical unicorn primitive may not exist all over the place. And in fact, it's pretty hard to come by. It's a pretty hard instruction to implement. It would be quite expensive, especially if those were like different cache lines and things like that. Now, conveniently, there's no double compare and swap, but there happens to be a 16-byte version of one. So, and in fact, this was actually an instruction that I can't remember which Windows operating system required it. Windows at some point asserted that they needed the 16-byte compare and swap, and all processors, Intel processors prior to that could actually not run that version of Windows because they needed this in certain places. And I don't recall which one it was. Do you know, Brian?
No, but I know they do the unlock-free.
Yeah, I mean, I can't remember which version of Windows it was. It wasn't really recent, but it might have been XP or something like that that said, really actually dictated a particular instruction in the processor to really efficiently deal with some internal OS data structures. So what I did here is I re-implemented the stack in terms of your suggestion, in terms of not double compare and swap, a regular compare and swap, but happened to be on 260, on a wide word, and I happened to put the pointer and the pop count value right next to each other in memory, which allowed me to do this 64-bit compare and swap. And that's exactly why Windows wanted this instruction, actually. But there's actually one other thing that's not safe here. What's not safe is that even though, while I'm in the data structure, and I'm accessing nodes in the data structure, if someone deletes that node, absolutely my compare and swap will fail. That's the whole point of it. But I'm accessing the old stop top's next pointer. What happens if the old top was deleted? That memory may be gone. So this data structure, if you assume that the callers free and repurpose the memory, which is a perfectly reasonable assumption, unless you're in a garbage collected language, this code is still broken. So a lot of the lock-free data structures work, for example, in Java collections, like Java lock-free, hash map, whatever, is in Java where things are garbage collected. And if the thread is holding a reference to this particular object, the garbage collector is not going to reclaim it. So in a garbage collected universe, in a managed universe, it becomes a lot easier to think about these lock-free data structures because you don't have to worry about this problem. If this is C, like I've written it here, old might have been deleted by the thread that deleted it. In fact, here, notice that I'm actually doing the memory management in the stack, and then I'm allocating the node on push and deleting it on pop. This memory's gone when I'm reading it if compare and swap fails. So I now have another problem. And the solutions now are starting to get more and more complex, right? Like I already needed a new machine instruction, or I needed a more advanced comparison operation, like if, unless I got this wrong, like load link store conditional to get this right. I'm now all of a sudden have to think about touching bad data, and here's my implementation that solves that problem, and it's starting to get a little gnarly, right? And the idea is to actually use what's called a hazard pointer. And a hazard pointer is every thread that enters a lock-free data structure, if it's going to access a node or an object, it maintains a local structure which says, here are the nodes that I'm currently looking at. So you'll see in my implementation here, when I enter the stack and I'm looking at this node, I write to the local thread's hazard pointer saying I am looking at, and in fact, actually, I believe this should be old, excuse me. I might have a bug. But anyways, if I'm going to look at an object, I write a note in my hazard pointer saying I'm currently looking at this. And when I'm no longer looking at it, I remove the hazard pointer. And so when a thread wants to delete an item, so notice here that I used to have delete here. Now I have retire. Retire is a function that then looks at all the hazard pointers of all the other threads. If it cannot find the object, it deletes the memory. So it's now becoming pretty tricky to implement a correct version of one of these programs. And by the way, everything in this lecture is assuming sequentially consistent memory. I have not put in any kind of fences or things like that I need to possibly get this right on a relaxed system like ARM. So the number of papers or people in the world that write high-quality lock-free data structures is relatively small. It's relatively small. It's a very hard thing to do. I'm going to skip a few, skip a few things, is that lock-free linked list insertion seems like it'd be a pretty easy thing to do, and I think you even actually proposed a correct algorithm for insert earlier, or one of you did. I can't remember who did. Which is, while my previous pointer is unchanged, or the previous link forward is unchanged, keep trying to insert me after the current node. And as long as, if somebody else got in there, that's okay. I'm still going to try, I'll wait till you're done, and I'll try again, over and over and over again. So lock-free linked list insertion, if that's the only thing you're going to do, is actually pretty easy. Lock-free linked list deletion, I'm going to refer you to the papers because I would need 30 to 45 minutes of lecture to actually kind of work through all the various cases, ignoring hazard pointers and ignoring all the other things. So there are some very good papers on this, and every year, a great project, somebody attempts, for example, a lock-free skip list or a lock-free malloc implementation or something like that. And they're very, very nice little challenging projects. Now here's my little disclaimer about the whole business, is that this is one of those things where often people go, oh, lock-free, that must be good. And they say, I have crappy code written with locks. I spend all this time to implement an awesome lock-free version, and things run much, much better than my crappy code written with locks. Right? Whereas if you actually just put some effort into fine-grained locking implementations, then the performance differences can be far less. But that said, that if you look at data structures in the kernel, if you look at data structures particularly in a lot of the Java collections, you'll see concurrent lock-free implementations of those. Because often those programs are written in situations where the web server is totally oversubscribed, and it matters if you get swapped out. If we're talking about high-performance computing, where we create exactly the same number of threads as the machine needs, then some of the advantages of lock-free data structures start to drop. So here are some experiments by a fairly recent paper characterizing the performance and energy efficiency of lock-free data structures, where they compared a queue, a deck, a doubly ended queue, and a linked list, and they took high-quality lock-free implementations, and they compared them in some cases to fine-grained lock implementations, at least in the linked list, exactly almost what we talked about today, the fine-grained locking. And you can kind of see some interesting performance results. So the x-axis is the number of threads. 1.0 is normalized to a p-thread that uses mutex locks. Probably, actually, I'm not sure. I'd have to go check the paper. I forgot now if that's a spin lock or if that's actually the heavyweight mutex lock. And so that's 1.0. And you can see that the lock-free data structures start to win at large thread counts, less than 1.0. And you can see that it's interesting in the linked list, the lock-free data structures lose at small thread counts because you've got all this overhead of trying to do it correctly. I mean, there's actually to very carefully order your data structure implementation. You have to do the compare and swaps and this and that. And if there's contention on the data structure, that means that every thread's doing compare and swaps and failing. And you remember from our test and set lock, that's trouble. And you can see that the lock-free implementations on the linked list, though, are like almost often the clear win. The linked list is like the really nice data structure for lock-free things for the reasons that we talked about in class. Interesting, you see the fine-grained locking version doing pretty well until the number of threads got really high. And then boom, performance just kind of goes off a cliff because of contention for something. I'm not sure what the contention would be here. So the story is not, oh, if you can figure out how to not use locks, you'll be much better. The blogs on the web are full of, hey, look, just use a spin lock with the appropriate backoff, and all of a sudden my simple implementation is within 20% of this, academic paper on lock-free data structure. So be careful on these things. Yep. Exactly. Yeah, I mean, you're going to have tons of write traffic, and that's probably what's going on here. I don't know what machine this was run on, so I couldn't hypothesize why. Lock-free or the lock? No, the fine-grained locking, one of the problems with fine-grained locking is to put a lock in every node. Like, that's annoying. And it's not just annoying, it's like a 50%. Like, if your linked list is just storing integers, that's a 50% space overhead to throw an extra lock in there.
But in that case, would it like fit in my cache line? Do I have to make like spare space so that it fit in cache line?
Oh, you mean to avoid false sharing on the locks? Well, if you assume that you have millions and millions of elements in your list, because presumably the list is big if it's a big system, they're gonna be spread out. So I wouldn't worry about that one so much here. So, yeah, why lock-free data structures? And just keep in mind that well-written code with fine-grained locking in some situations can be very fast. Lock-free data structures are a really beautifully elegant solution to some of these problems, but they are very error-prone and very difficult. And most of the time, it's like a bunch of people worked forever in the standard library of Java or standard library of C and produced a nice, high-quality implementation, and it still doesn't work on ARM or something like that. So, like anything, you need to evaluate when it makes sense to be a good idea. And I should point out that lock-free designs does not mean contention-free designs. Compare and swap may fail indefinitely, and you still have performance problems, but sometimes it can be a little bit more elegant. So there's a lot of, like, if you just Google lock-free data structures on the web, like, there's no shortage of really interesting stuff, like blog posts of people saying, okay, I tried it this way, and then I tried it this way, and then I tried it this way. Really cool things. And then the last thing I want to point out to close up, let me go back to that other is that what I want to talk about next time is the following. Imagine you have a shared variable. Imagine you have a stack or a linked list. And we're kind of getting at this with lock-free data structures. A lock-free data structure is sort of a philosophy of, I'm going to go ahead and do it. And if something bad happens, I'll detect it right at the very end and kind of try again. And if you take that philosophy to the extreme, you could just say, how about I just assume nothing ever bad will happen? You know, like maybe most of the time, maybe I'll be fine. I've got like millions of elements in my list. I only have 2 threads. You know, what's the chance that they're all going to be touching the same element at the same time? Test harness won't find it, so it's probably fine, right? So you can think about a lock-free data structure, a lock-free approach as sort of being optimistic. I'm going to move into the function. I'm going to start doing the thing. And I'm going to have mechanisms that I design in my code to detect when something goes wrong. So what I want to talk about next time is to actually say, you know what? How about we just declare the parts of the program that we want to have occur atomically, and let's have the hardware tell us where stuff goes wrong. Where if compare and swap or load, link, store conditional tells me, has anybody written to these values, the single value that I care about in memory, a single address? What if the hardware could do it for any of the addresses that I happen to touch over the duration of this big atomic operation? And if any of them get touched, hardware will let me know, and I'll just start over. I don't have to do the detection myself in software, or at least at the application software level. And that's very much like the notion of a transaction in a database, right? Try and do this, and it needs to all happen or not happen at all. And so next time, I want to talk about hardware support for synchronization, transactional synchronization, where you're just going to say, look, I want all this to be atomic. It's a push, it's a pop. You let me know if anybody else decides to do anything related to the addresses that I'm touching. And hardware is going to help you with that task. And so it's a much more modern way of thinking about things. And it's sort of, the jury is still out on whether or not software written using these transactions will be more efficient or easier to write than traditional locks, or well, certainly easier to write than lock-free data structures, because this kind of stuff only popped up in Intel hardware in like 2014. So this is going to be very, very, very new things. Okay, so that's 420.